Hello and welcome to the course of Introduction to Astrophysical Fluids. Now here df dt not equal to 0. Okay. What is the meaning of that? And of course, this is when traced along a particle trajectory. What is the meaning of that? If the system allows collisions, then basically that f changes for a collisional system if RUT can change because of two reasons. Number one is some particles originally having velocity u may have other velocity just after collision, right, thereby leading to a loss in FRUT. So, F is the number of single particle states, okay, in the phase space volume. F is the density of single particle states in the mu space, that was the definition. So, you can see that if there were no collision, then F would have just evolved dynamically, okay, and according to some law, like let us say some R, maybe a law of let us say R could be like varies as t to the power 3 by 2 for example, then you know like if the particle is now over here, then after some time where it will be, and then you can also calculate u, right, and you can also calculate so R dot, okay, if you know this type of dependencies, and then you can also say that what will be its velocity at some subsequent interval. Okay. Now, the problem is that if collision comes, so this is something which is not expected, okay. This inhibits a normal evolution. Okay. So, that means if the particle was evolving according to some evolution, then the problem is that although we are saying that kinetic energy, momentum all are conserved before and after the collision, if you are concentrating on a single particle, basically before and after collision its individual momentum and kinetic energy, they are basically changing. Okay. So, remember for a single particle, both linear momentum and energy and kinetic energy changes before and after the collision. So, it simply says that if the particle was belonging to the particles having velocity u for example, okay, then what happens just after the collision. So, just after the collision in general we assume that the particle is momentarily localized, that means just after the collision what happens, its velocity changes, but it does not still leave the place. Okay. So, its position will be still r, but it will have some basically different velocity. Okay. And if this is true, then basically you can easily understand that this will lead to a loss in F of R, U and T, okay, because now the particle is moving to another club of particles having some velocity, let us say u1 or rather u prime, sorry, I think u prime. Okay. After the collision I used the primed coordinates, and then you can say now the particle is now belonging to f of r u prime and t. Okay. So, in the same way another source of loss is simply, or actually loss, another source of change is simply that some particles originally having, this is actually a gain, originally having some other velocities can attain velocity u after collision. So, this is a gain in f r u t. Okay. These two effects are now non-zero. So, schematically this can be written as df dt cube x d cube u. So, if you just remember this df dt now multiplied with d cube x d cube u. So, f d cube x d cube u is nothing but the number of the particles in this elementary volume of phase space, or rather mu space. Okay. And d dt is the change of the number, okay, with time, of course along a particle evolution trajectory. Okay. And that will simply now be written as minus C out plus C in. So, if you remember, this is nothing but the number, I mean the rate of the particles gained or lost, okay, through collision, and that we can classify into two classes, one is the loss, one is the gain. Now, we assume beams of particles. So, before we assume two beams of particles u and u1, now we will be interested in having beams of particles having velocity in the infinitesimal range. One is that u2 u plus du, and another is u1 2 u1 plus du1 respectively. If you do that, then delta NC, if you remember the definition of delta NC, that was this n times n1 u minus u1 modulus sigma omega d omega, then you can easily write now delta NC will be equal to f of r u t d cube u. This definition is very interesting, you can see. So, f is the number of particles per unit phase space volume. Now, if it is just multiplied with the number of d cube with d cube u, it simply says that this is the number of particles having position r, but having velocity ranging from u to u plus du. Okay. And that is exactly what we are seeking for. Okay. Another is for the second beam r u prime t, no, not u prime, but sorry, r u 1 t d cube u 1. Okay. Again the rest was just u minus u 1 sigma omega d omega. Okay. Now, you remember that now we are having two beams where the particles having the velocity in this range and in this range. Okay. But that will simply change the number densities, but the relative velocity will not be changed by that. Okay. So, this basically can be related to C out by this definition. I do an integration over u1 and omega delta n c times d cube x. Okay. Now, what is the meaning of that? Why I did that? So, I just say that if I now integrate this thing, so you see that this has 3 differential part, right. One is d cube u1, another is d omega, right. If I say that I integrate already on u1 and omega, that simply says that, and also I multiply this with d cube x. So, finally, dnc, okay, dnc multiplied with d cube x and integrated on u1 space and omega space simply gives us the number of loss of the particle or the number of change, I mean the change of the number of particles changed or lost or gained, okay, per unit time from the volume element d cube x and d cube u, right. Because if you just see this one, now if you integrate for example this thing with u1 and omega, then you will have 2 integration, and this u1 will be, I mean this will be integrated over u1. So, this part will be integrated. So, there is a u1 as well, and the omega dependent part will also be integrated. So, finally, you will have something where you will just have the number of the particles, okay. dnc is the number. So, this is the nothing but the number of collisions, okay, per unit time within phase space volume d cube u. And if you now multiplied with this whole thing with d cube x, then finally you will have number of collisions per unit time within phase space volume d cube x d cube u, and we are saying that that is exactly equal to C out, right. If this is true, then finally we can write that C out is nothing but d cube u d cube x. I just make them out of integration because they will not see the integration. If R u t, if R u 1 t u minus u 1 sigma omega d omega d cube u 1. Okay. So, that is the definition for C out. In the same way, basically you can also calculate just by tracking the collisions in back process. That means you are you can think that as the collisions are elastic in nature, so there is no dissipation. So, whether the the collisions are taking place in a forward manner or in the backward manner, they will behave identically. Okay. So, basically then you can see that if you now consider the collisions of 2 particles which are coming and collide with velocities u prime and u 1 prime, and after collision they have the velocities u and u 1. Okay. So, if you consider this type of collisions, okay, in a backward direction, then basically you can write or you can obtain an expression for C in, which will simply be d cube x d cube u prime integration d cube u 1 prime integration sigma prime omega d omega. So, sigma prime omega is just the angular distribution for the backward collisional process. Okay. U prime minus u 1 prime times if, so F is nothing but R u prime t, and this will be F R u1 prime t. Okay. So, this is the definition. Okay. Now, remember that we have a binary collision. We have binary collision only, which are elastic in nature, right. Then what is the good news? We have, first of all, u plus u1 is equal to u prime plus u1 prime. Before and after the collision, this is nothing but the principle of conservation of linear momentum, because of all the particles are having identical mass. So, mass is not there, and we can say half u square plus half u1 square will simply be equal to half u prime square plus half u1 prime square. That is principle of conservation of kinetic energy. Okay. Again, mass is not there because this is cancelled. If you do this, this can be simply left to you as an exercise, that you can show that it leads to a very simple result. This is equal to u1 prime minus u prime mod. So, u1 minus u vectorial mod is equal to the magnitude of the difference of u1 prime and u prime. Okay. So, and if you remember, I do not know that if you are habituated with this mechanics of collisions, this is nothing but of saying that the coefficient of restitution is equal to 1, right. So, this is also another property of elastic collision. Okay. Finally, we consider the phase space of two colliding particles. Okay. Only two colliding particles are there. So, if their interaction can be described by a Hamiltonian, then so that is something not very evident. So, finally, we consider the phase space for two particles. Okay. Only two particles, okay, which are colliding. And if we say that under the condition that this two particle system can be described by a Hamiltonian, okay. So, usually this is only possible that if their collision is taking place under some central type of force, where the potential is basically depending on the relative distance of between them, or I mean some other system, so that you can write, I mean the final thing is that you can write a Hamiltonian for this two particle system. Okay. Now, remember that these two particle systems are actually colliding with each other. Okay. If we write a Hamiltonian, then the corollary of Liouville's theorem simply says that d cube u u1 will be equal to d cube u prime d cube u1 prime. Again a very important result. Okay. And finally, you can also say that sigma prime, so sigma prime and prime omega will be equal to sigma omega, just supposing the collisions are reversible. That is true because we do not have any source of irreversibility like any dissipation or anything. Okay. Then using all these things, finally you can write using all the above conditions, we can write C in equal to d cube x d cube u integration d cube u1 integration sigma of u omega mod of u minus u1 f prime f1 prime d omega, where f prime simply means that it is nothing but f r of u prime, I mean f of r u prime and t, and f1 prime is f of r u1 prime and t. Okay. So, using the expressions of C out and C in, we can finally write, have del f del t plus u dot f plus f by m dot divergence in velocity space, I mean gradient in velocity space of f will be equal to integration d cube u1. So, it will be minus C out plus C in. Okay. So, you plug both the values of, so C in you can get here and C out you can get from this one, right, this one. Okay. So, if you do that, so finally you can have integration over sigma of omega u minus u1 modulus, and finally I have a factor which is f prime f1 prime minus f f1. Once again f is nothing but f of r u t and f1 is nothing but f of r u1 t. Okay. So, you see these are the distribution functions after collision, these are the distribution functions before collision. Okay. So, finally you have this expression which is known as the traditionally collisional Boltzmann equation or simply Boltzmann equation. Whenever we say Boltzmann equation, it simply defines the Boltzmann equation with the collision term. Okay. So, this is known as Boltzmann equation. Okay. So, here basically in this lecture, after deriving the collisionless Boltzmann equation, we derived a version of Boltzmann equation where we extended the Boltzmann equation for collisional system. Okay. But the collisions are of very specific nature, they should be binary and they should be elastic in nature. Okay. Thank you.